Welcome everybody. So this week I'll be continuing with from where I left last class. So last class we saw about we just before concluding the last class we saw about the atomic orbital, molecular orbital, etc. How the electrons are stacked in the shells, the subshells, the quantum numbers, etc. All those things we saw. So we'll continue in that vein, but this time we'll be focusing more on electromagnetic radiation because that's very relevant to what we are going to do in atomic absorption spectroscopy. So we look at the behavior of electromagnetic radiation, how it interacts with matter, etc. Okay, so I'll just start from there. Today we'll also look at some questions. Okay, so what is electromagnetic radiation? It is basically energy that is transmitted through space at the speed of light. EMR or electromagnetic radiation is energy transmitted through space at the speed of light. And you know what the speed of light, right? It's denoted by C. It's 3 into 10 to the power 8 meter per second, right? Like you also must be familiar with Einstein's E is equal to mc square formula. There also C is the speed of light. You'll use that in nuclear physics and all. So I'll just show you one. Okay, so this is electromagnetic radiation. See any of the pictures here. The wave propagation, if it happens in this direction, it is perpendicular to the magnetic field as well as the electric field. Okay, so electric field, magnetic field are perpendicular to each other, and both are also perpendicular to the wave propagation direction. So that is how it goes like. So electromagnetic radiation, it has two perpendicular components. I see that nobody has joined the class today, so I'll go at my own luxurious pace. Also, like the forum was quite empty. I just checked it yesterday. No questions were asked in the forum. So yeah, please make sure of that. Uh, if you have any questions, you can ask in the forum, and I'll be checking it every week once. And if possible, I'll be addressing that in the class. Okay. So it has got two perpendicular components. One is the electric field, denoted by E. There is the magnetic field, denoted by B. Let me put it in words, then I will tell you. Okay, so as I showed you in the picture, these two fields are perpendicular to each other and also perpendicular to the direction of wave propagation. See in the picture. So here, there's a number of videos on YouTube also. You can check how they oscillate. So what are the examples of electromagnetic radiation? They can be visible light. Again, if you see a rainbow, you'll see that the white light, it is composed of 7 colors: vibgyor, violet, indigo, blue, green, yellow, orange, red. So those are the components of visible light. Okay, UV rays. So these are rays emitted from the sun. Uh, Generally quite harmful above, especially in tropical zone. If you spend too much time in the sun, you may have cancer probability and all. But it's also necessary for vitamin D and all. So you have to strike a balance. Okay. For instance, above Australia, like there is ozone layer depletion, because of which this UV rays uh, unopposed high concentration of UV rays in the people, and skin cancer is very common in Australia. So like that, UV rays and infrared like you use in military radars and all, right? If you follow cricket, there is something called hotspot now, especially in matches in Australia. They show you hotspot also along with hockey. So wherever the ball hits a pad or the bat, basically it's a heat signal. It detects the heat signal and shows whether that ball has touched the pad or touched the bat. Okay. Uh, Radio, like radio waves. Earlier, like we used to have radios and all for before this television era, mobile era, we had radios and all to follow cricket commentary or music. Okay. Microwave. You must have seen it used for cooking and all, for heating the food. Basically, it makes the water molecules in the food vibrate, and because of the vibration, it releases energy, and because of that energy, it heats up. So it's like that. X-rays, like this, everybody must have done an X-ray at some point, right? To check whether you have a fracture or some problem in your bone. Then another is gamma rays. These are more common in radioactive minerals, materials, or nuclear reactors. Okay. So these are examples of electromagnetic spectrum. So electromagnetic spectrum, like uh, there is something called wavelength. Okay. So this electromagnetic spectrum has got wavelength as well as particle-like nature. Wave meaning like it'll oscillate like this, where this is the amplitude of the wave, and right, this is amplitude, and this is the time period, one cycle, going till here, coming zero, reversing direction. It's like a sine cos wave, right? So yeah, this length is the lambda or the wavelength. This is amplitude, E naught. So depending on the wavelength, there are a number of uh, subcomponents of electromagnetic radiation, which I just talked about now. So I'll just make a table telling what rays in what wavelength and applications and examples, etc. Okay. So let me just write it here. So I asked you to do a homework also last class, I remember. But anyway, I'll be doing it. Sorry, I have a cold, so this cough. Region, wavelength, and applications or examples. We'll make a table. Okay, so we will start from low wavelength to high wavelength. So low wavelength will be like this, right? Low wavelength means like it will be like this. High wavelength will be like this, right? So low wavelength, the shortest wavelength of the electromagnetic spectrum is gamma rays. So wavelength is generally less than 0.01 nanometer. So we can say 0.1 Armstrong, because 10 10 10 Armstrong is 1 nanometer. Angstrom, sorry. These examples or applications you can find it in nuclear physics or in astrophysics. So like in space, a lot of gamma rays are emitted, okay? And studying those wave patterns, you get to know about stars, galaxies, how they are formed, the geometry of the black hole, etc. All that stuff. So that's how they use it. Next is X-rays. This wavelength is 0.01 to 10 nanometer. Where is it used? It is used in medical imaging. Especially fracture and all. Sometimes just to check your chest cavity, they may ask you to do X-ray. A little bit above than this is what is known as UV rays. UV rays is 10 to 400 nanometer wavelength. An application or example is one is sunburn. Like if you're exposing your skin to large amount of time, especially in the tropical zone where the UV levels are generally high, you can have sunburn. So that's why you wear sunscreen. Block the UV rays and protect your skin. And another thing is disinfection, where you use UV rays to kill all the bacteria and germs. Okay, so in some foreign countries and all, it's quite common to use UV rays to clean the water samples. Even public swimming pools, etc., they will just use a UV ray and kill all the microbes. In India, like of course, it's not used because it's a very costly option, but it is used elsewhere. Next is visible light, 400 to 700 nanometer. Examples are what? Human vision, rainbow. Remember WebGeo? Sorry. Okay. Now as we further increase this, I'll upload all these notes, so don't worry. But if you don't take notes, you can always refer to the PDFs. So after visible light, what we have is infrared, IR. It's like zero point 0.7 to 1000 micrometer. Micrometer is like 1000 times bigger than nanometer. So example is heat. You can find it in hotspot technology in cricket. Also used in army, radars and signals, etc. Hotspot, I'm sure you must have seen these things. Okay? Like these kind of things, no? In Australian broadcast and all. Like if the wherever the ball is hitting the bat, because of heat generation, this shows up in infrared cameras. So this is a special type of technology to see whether you got inside edge, outside edge, whether bat has struck the ball in for LBW decisions, etc. Right? What is next? It is microwave. Has got very high wavelength, 1 millimeter to 1 meter. 1 millimeter to 1 meter. Where is it used? Cooking. You have this microwave oven set. Sorry, it doesn't come out to me. My handwriting is very bad, okay? So I'm very sorry for that. Next is what? Radio waves. This wavelength is above 1 meter. Example is like radio set, where you can listen to music or some RJ playing some stuff. So only this visible region is detectable by the eye, okay? Rest and all are not detectable by eye. Even though they are also waves, but maybe some other animals can, they may have their vision capable of detecting much more uh, broader range of wavelengths, but human eye can only detect till whatever is in the UV range, sorry, visible light range. Just to give you an idea of the units used in electromagnetic ray description, uh, in the nanometer range, just some extra information I'm giving. Nanometer is common in UV and visible, right? Check the ranges. So in this range, spectroscopy generally deal with nanometer. Hmm. Angstrom, historically, it's more common in X-ray region. Micrometer, more used in infrared spectroscopy. Okay, so there is some other stuff like uh, there's something called wave number. Okay, its unit is just, it's just 1 by lambda, where lambda is a wavelength. So lambda is a wavelength length. It has got units of length. Example centimeter. So if this is centimeter, lambda's units. Wave number will have units of centimeter inverse. Okay, and there's something called electron volt, which is a unit for high energy radiation. Right, especially for gamma rays. We talk in terms of electron volt. Hertz is a unit for frequency. Like if you have some radio, right, they will always tell you to tune to a frequency. 98.4, 102 point this, 105 point something, 92 point something, right? 92.7 red FM radio, like that they will tell. So her frequency is basically, it's inversely proportional to lambda or wavelength. Higher the wavelength, lower the frequency. Lower the wavelength, higher the frequency. Basically, it tells how much how many times it's repeating. Okay, so if this is one wavelength and this is another wavelength. So in this particular amount of time, this is repeating more number of times than this, right? So this has got higher frequency. This has got higher wavelength. So coming to the next part. Okay, just remember one the thing that Electromagnetic radiation has a dual nature, both wave-like as well as particle-like nature. So Einstein basically that's what he won Nobel Prize for to prove that the light is composed of particles. That's the photoelectric effect, right? It's a misconception that Einstein won Nobel Prize for relativity, even though he's more famous for relativity, but he won Nobel Prize for the photoelectric effect, where he told that light is composed of particles. Those particles are known as photons. So what are the wave properties? Wavelength lambda, frequency nu. This is what wavelength, velocity of that wave, and amplitude. Okay, so a couple of equations. I'll just tell that velocity of a wave is just frequency into amplitude. Sorry, wavelength. So this has units of second inverse. This has unit of length. So when you combine them, you'll have units of velocity, meter per second. This is the wave equation. The other thing is E is equal to h into frequency. Here we are assuming that we are looking at the particle property. Okay, the earlier one was the wave property. We are combining both wave-like nature and particle-like nature. So this comes under particle properties. Because I told you now, because that EMR is comprised of photons. These are discrete energy packets. Can anybody tell me what H is? You must have come through this equation many times, right? Especially in school and all, highest secondary. H is what is known as the Planck's constant. Right? What is the value of Planck's constant? Its unit is 6.624 into 10 to the power minus 27 per second. Right? And here in this equation, what is E? E is the energy of the photon. Nu is the frequency. So I already told you from the wave equation that velocity is equal to frequency into lambda. Here velocity is we denote by c, speed of light, 3 into 10 to the power 8 meter per second is equal to frequency into lambda. Therefore, what is frequency? It is c by lambda. You substitute that in this equation. E is equal to h into nu or h into c by lambda. Okay, so this is the energy of the photon. We are combining the wave-like nature and particle-like nature of light over here, right? So this equation you may get right to solve some problem or something. Talking about vacuum here, that's why I took C. For speed of light in vacuum is 3 to 10 to the power 8 meters per second. Speed of light will be different in different medium. Let us just talk about vacuum because photon, for instance, it releases from the sun and comes to Earth, right? It travels through vacuum, empty space. And after that, obviously, once it encounters a medium, light bends it up. That is what is the refraction. So yeah, what is urge here? H I told that H is equal to 6.624 6 to 4 into 10 to the power minus 27 Earth second. So Earth is just the unit of energy in CGS unit. You must be aware of various units, right? Like SI unit is systems international, meter, kilogram, second, etc. So Earth is the CGS system. What is CGS system? It is centimeter, gram, second. So basically, how Earth is defined is energy required to move 1 gram mass by 1 centimeter using a force of 1 time. Okay, so that's how it is defined. You just replace it by kilogram, meter, and Newton, you'll get joule. So basically, 1 Earth is equal to 10 to the power minus 7 joules. Just these are just units of energy. So H is basically 6.627 into 10 to the power minus 27 Earth second, or convert Earth into joule, 6.627 into 10 to the power minus 34 joule second. Okay, so there is something called EMU also. I'm not getting into all of that. It stands for electromagnetic unit. It's a system used to measure electromagnetic quantities like current, field strength, magnetic field, etc. For instance, current is ampere, magnetic field is oersted, magnetic induction is Gauss. I'm not getting into the details of that, so we'll skip it for the moment and we'll go to the next part. So, what's the spectroscopic relevance of all this? Spectroscopic relevance is that it measures, spectroscopy is necessary for AS. So, basically, it measures how atoms absorb light, right? Absorption occurs only when the photon energy exactly matches energy difference between atomic states. And this principle allows precise quantification of metal ions in a sample. So that's the significance of uh, relevance of this for spectroscopy. Okay. I mean, whatever you have been doing in the last couple of classes. We'll come to that later. But first, what I'll do now is that I will, since none of you are in class, not an issue. Can just I'll also after this class I'll upload one Word document containing some questions, so you can refer to that. So this one I'll be uploading. So just check this and like there are two sets of questions. One is like the previous year's assignment problems. The other is I made some problems over here. So these two just sit and try to solve them. We take a 10 minutes break, okay? 18 questions to try to solve. After I come, we will solve it, okay? So yeah, just refer to this question paper and try answering the questions. Thank you. Hope you guys gave them a shot. So we'll just discuss the answers with you. Okay. The first question is the procedure for environmental pollution control involves the determination of pollutants and extent of pollution, technical intervention, post intervention evaluation. So this is from his very basic first class. So he also made note of all this. So the answer is D, all of these. Because pollution control is a process which involves assessment or how much pollution is there. Seen, I give an example of arsenic in water sample, right? So how much arsenic is there in the water? Second stage is using some technological tool to intervene and reduce the pollutants. Okay, using some membrane exchange, ion resin, something to do. And then finally, that once you've treated the water, you check the effectiveness of treatment. So post-intervention evaluation. So correct answer is all of these. Second question is neutrons are stable in the nucleus, outside the nucleus, in the reactors, in the environment. Again, directly from the notes, they are stable inside the nucleus. Second question, right? So another fact is that the free neutrons, that is the neutrons outside the nucleus, they have a half-life of 14 minutes, and they decay into proton, electron, and antineutrino. So like not necessary all these details. Just know that only inside the nucleus is stable. Second is third one is also directly from his notes. Electronic excitation energy ranges from dash to dash. What do you think the answer should be? Four options are given. Huh? This is the answer. This is actually last year's assignment. So 35.71 to 700 kilocalories directly from the notes. What about neutrinos? What are neutrinos? See, neutrinos, this question is from last week's assignment, okay? This you can say that they have mass and no charge or no mass and no charge. Both I feel are the correct answers. Okay. So in his notes, he told me that uh, in the sorry, last week's answer key, it is that no mass and no charge. But I feel that it can be mass and no charge as well as no mass and no charge because you can't say it as protein and mass. Okay. Because one, it's a very old-fashioned view that neutrinos are massless, right? But more modern experiments, they have shown that it has got a very tiny, tiny, tiny amount of finite mass. Like it's even compared to electron, its mass is much lesser. Still, we cannot tell that it has got zero mass. Okay, so just make that point over here. They are chargeless, that is true, but related to mass, once thought to be massless. Of late, it is shown that it has got a very tiny mass, like 1/1000th of the mass of an electron. Recent experiments show that it is not massless. So in my opinion, either you do the third option or the fourth option. Both should be correct. But the answer key last year had that it has got no mass and no charge. That also I will tell you very clearly. So what's the next question? Next question is electrons cause ionization in gases, darken the photographic plates, yield X-ray when bombarded against suitable targets. So the correct answer is all of these. Right, okay. Anyway, we'll go to sixth question then. So electrons do cause ionization in gases because uh, they can knock out other electrons, because of which ions will be forming. They do darken the photographic plates, like that is J.J. Thomson's experiment, he showed it. And the third option is also true. They yield X-rays and mobile against suitable targets. Let's go to the fifth one. High neutron is to proton ratio in atomic nuclei attains stability by radioactive decay process. This is achieved by water. The correct answer over here is beta emission. Yes. Mm. So this again is from Sir's notes directly. So when there is very high neutron to proton ratio, the nucleus converts a neutron to a proton by beta emission. Okay. So basically the neutron gives rise to proton plus electron plus antineutrino. Right? And this lowers the N by P ratio and brings the nucleus towards stability. All of these are mostly from Sir's notes only. Okay, so next question. Spectral series exhibited by Lyman, Palmer, that one, right? Spectral line series exhibited by Lyman, Balmer, Paschen, Brachet, etc. is true for which one? Okay, so this is again from the notes. It's true for hydrogen, helium, lithium, and beryllium. Directly from the notes, okay? Electronic transition in molecules are characterized by excitation from four options are given: bonding to non-bonding orbitals, non-bonding to bonding, bonding to anti-bonding. Fourth option is non-bonding to anti-bonding orbitals. So here the answer is 3. Because it cannot go from non-bonding to bonding, right? If you look at the definition of all of this, I think this is from previous class. See, bonding means there is a constructive overlap which increases electron density between nuclei, and anti-bonding is destructive overlap or creates zero electron density. So it can go from bonding to anti-bonding, right? Because bonding is where there is electron density. Anti-bonding, there is no electron density. So from here to here it can go. But can it go from bonding to non-bonding? Non-bonding means lone pair, okay. So types of electronic transition molecules is it can go from lone pair to anti-bonding, okay. So okay, so non-bonding to anti. So I think both 3 and 4 are correct over here. Okay. So because I think this I covered in the previous class, I don't have the notes right now. The other two don't make sense, okay. Bonding to non-bonding and non-bonding to bonding don't make sense at all. So you only imagine what can the transition happen. It can come from sigma to sigma square it can go. Pi to pi square it can go. That means from bonding to anti-bonding it is going. That is a third option. Or it can go from non-bonding orbital to anti-bonding orbital. Like n to pi square it can go, or n to sigma square it can go. There's no other option, right? So refer to the previous class notes, okay? So but I think both should be correct. Maybe if you doubt, like next class you can further go deeper into that. I have to refer to the previous class notes. Some I don't have them right now. So what is the ninth question? Both circular orbits are the extension of Sommerfeld elliptical orbits. So I think it is true. It's an extension, you can say. Though Sommerfeld followed Bohr, but still, if you say Bohr came first, then only Sommerfeld came first. But what Sommerfeld basically said that is that you can include elliptical orbits to better explain this orbital orbits for electrons. Bohr said it is circular. Sommerfeld says it's elliptical. So elliptical with the minor axis and major axis are same. That's A is equal to B. Ellipse becomes a circle now. So basically, even though Bohr's model came first, you can tell that it is uh, using circular orbits for electrons, which is special case of elliptical orbit where A is equal to B. So like that you can justify. So the answer can give it as true. Okay. So electronic radius of atoms are of the order of, yeah, it should be an order of angstrom, a few angstroms. So these are the last uh, year's assignments. Maybe if you're doubting these things, like just raise it in the forum, or you can even ask me on WhatsApp or something. Okay, but I would prefer you raise it in the forum because then other students can also see it, and if they also have the same doubt, it can be clarified for more than one person. Okay, so next part is what does the principal quantum number determine? Number of electrons, shape of orbital, energy level and size of shell, orientation of orbital. What does n represent? So answer should be 3. The energy level and size of the shell, right? Because there are 4 quantum numbers I said, n, l, m and spin vector. So 4. N defines the energy level and the average distance from the nucleus. Shape is determined by L, orientation by M, and direction of spin by S. Okay, so this will all be covered in last class. the number of orbitals. So yeah, what's the answer for this? Answer is three only. Sorry. Here, three only. Number of orbitals in a shell with principal quantum number is how much? It's n square, right? And each orbital has got two electrons. So total number of electrons is 2n square. What transition involves the greatest energy change? So obviously it is n infinity because the larger the gap between the two levels, more the energy will be, right? Larger the energy gap, greater the energy change. So uh, 4 to yeah. For instance, for 2, 3 to 2 will be less than 4 to 2 will be less than 5 to 2 will be less than dot 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 will be less than infinity to 2. So infinity to 2 is the highest drop you can imagine. Electrons in s orbitals. Four options are given. So what's the correct answer? All of these, right? All of these. Why? Because s orbitals means L is equal to 0. Okay. And if L is equal to 0, that means no orbital angular momentum. And if L is equal to 0, M can go from minus L to plus L to 0. M is also 0. And spherical symmetry is also there in s orbital. So occupy spherical regions around the nucleus, right? And won't be affected by magnetic field also because M is also equal to 0. There is no split in the Zeeman effect. Electrons should have spin magnitude, right? Because that is, yeah, I think 3 won't be the correct word. Only 1, 2, and 4. Because electrons will have spin, right? So that should give rise to magnetic moment. Okay, so the total number of magnetic quantum number values for D subshell is how much? So what is D? D is like at L is equal to 2. So at L is equal to 2, M can go from minus 2 to plus 2 through 0. So it's minus 2, minus 1, 0, 1, 2, 5. Answer is 5. The wavelength of electromagnetic radiation is inversely proportional to what? Its frequency and energy, right? Because I already explained to you that higher the wavelength, lower the frequency. They're inversely proportional. And if you see the equation, energy equation, E is equal to h into c by lambda. So E goes as 1 by lambda. So it's inversely proportional to lambda. So both energy and frequency are inversely proportional to wavelength. Which of the following units typically used to express IR wave number? You can refer to the table, right? Centimeter inverse. Wave number is like what? 1 by lambda. According to wave theory, a complete cycle of EM radiation is defined as 360-degree phase. Now, easy. So, moves from 0 to 180 and then ultra direction, like a sine wave. So, 0 to 2 pi radians. Okay, so I'll anyway upload this. Before we move to the next section. So, let's see how much time is left, whether we can cover it today. 1 or 2 minutes. Maybe we can do a little bit. So, I'll be introducing you to some concepts about how electromagnetic radiation interferes with matter. answer my questions, okay? And before that, and after that, I'll call off the class. So we will take a 5 10 minutes break, and 5 minutes break you take, and then we'll start the class. We'll resume the class. I will start off with the interaction of electromagnetic radiation and matter. Basically, just give you a few definitions before we go off the class. And then next class, like, we will go a bit deeper because it's now we are slowly getting into like the theoretical concepts of atomic absorption, AES, everything, how the instrument is modeled, etc. So we will, with this class, like we finish off the introduction part. So that from next class we can like get into the meaty portion of what this AES is all about. So I already defined you like what is EMR or electromagnetic radiation. We already saw that. I also told you what photons are now. Basically, photon is what particles of electromagnetic radiation. I'll use a more technical term now. Quantum of electromagnetic radiation that carries energy proportional to its frequency. Okay, and the energy of a single photon, it's given as E is equal to h into frequency, or hc by lambda. I already told you that h is Planck's constant. What is frequency? What is speed of light? What is lambda, etc. Okay, so this is the energy of a single photon. This we already saw. Next, we will look at some definitions. Okay. So, what is refractive index? First, define it. Okay, so refractive index is a measure of how much the speed of light reduces in a medium compared to vacuum. It's given by n is equal to c by velocity, where velocity is lambda into frequency. Which brings me on to the next definition. What is dispersion? Dispersion is basically the variation of refractive index, that is n, with wavelength. See, light is composed of 7 colors, right? Visual. And each of those colors slows by different amounts in the medium because the refractive index is not the same for all the colors. Uh, Blue slows down more than red, and so blue bends more, and different colors bend by different amounts. So if you see a light through a prism, okay, so White light comes like this, but when it is exposed to a glass prism, each of the wavelengths of white light, because white light is composed of seven colors, each have different wavelength. So outside they are traveling the same velocity, but when they enter into the glass, each of them slows down by different amount because each of them has got a different refractive index. Okay, so blue light slows more than red light, violet light slows more than blue light. So if it slows more, it bends more. Red light doesn't slow down that much, so it's more or less the same path. Okay, so least deviation is red light, most deviation is violet light. Okay, I'll just write it in terms of words now. Because these things will be components of the AS machine. That's what I'm telling. Okay, so light of different colors stored on with different amounts in a medium because the refractive index is not the same for all colors. Blue slows down more than red, and all the different colors light by different amounts in that medium. Next is intensity. Okay, next up, what is intensity? Is the power emitted per unit solid angle. So unit solid angle. Okay, so if you look at a laser and compare it to a torch, the laser's angle of emittance is much less than the torch, right? So the laser is more high in intensity, even though both may be same power, using the same amount of power, but laser is much more intense than a torch. So that's what intensity comes. Or if you take a torch, you shine it towards your ball, okay? As you come closer and closer, you see a very intense spot, right? When you're far away, it does not light up that well. But as you come closer and closer to the wall, you see a very intense yellow light because the angle is reducing as you go closer. What is scattering? Scattering is the redirection when it interacts with solid particles. Redirection of electromagnetic radiation due to interaction with particles. So if you put some water in a tub, okay, or say in a glass, and you put some shiny particles into it, then if you shine light at it, you will see that even the surrounding area glows faintly because the light is reflected by those particles. That is scattering, okay. Another important thing is polarization. It's basically restriction of EM waves to one plane. Okay, so light is coming in this wave kind of pattern. You put some slits inside, which allows only vertical uh, component of the phase to pass through, right? So restricting the light beam in such a way that only one plane of light can pass through. So this is polarized light. This is what is polarization. What is diffraction? Bending and spreading of EM waves, electromagnetic waves, when they encounter speckles or slits. Okay, so this is diffraction. When this wavelength, this light wave, it interacts the slit, okay? It bends and spreads throughout. This is what is diffraction. And I want you to just do a homework, okay? There is something called chromatic aberration. So just look into it. So because in lens based imaging, that's a distortion due to dispersion, okay? Because of which there is a problem called chromatic aberration. When we discuss the components of AS, we may touch upon this part. Okay. Polarization, I already told you that the EM waves will vibrate in many directions, but if you restrict them to one plane of vibration, that is polarization. Refraction also I told you. When there is an opening, light bends. Some equations I'll just tell you right. Okay. So there is something called Snell's law. So this is incident light in one medium. This is another medium. Okay. See, this is water and this is air. So it to the normal, it's incident at an angle of theta one. And because of refraction, it goes at theta two. So Snell's law says that n1, that is refractive index of medium one, so sine theta 1 is equal to n2 sine theta 2. So this also you can touch upon in the homework. What is Snell's law? You can. Basically, it's a principle that relates the angle of incidence and angle of refraction to the refractive indices in the two media. n1 sine theta 1 is equal to n2 sine theta 2. Where n1 is the refractive index in medium 1, n2 is the refractive index in medium 2, theta 1 is the incident ray angle in medium 1, theta 2 in medium 2. Okay. If you want, you can just go through Raman scattering also. Or like if you want, you can read these things. The other thing is that I just want to clear a misconception that people generally think that the high energy photons appear brighter than low energy photons, but it's not correct. Brightness is it's a quality that you perceive, okay, while photon energy is a purely physical quality. So power of a light source is number of photons per second into photon energy, and photon energy we get from the E is equal to hc by lambda, okay. So make that distinction very clear that just because it is brighter, Don't think that it is more in an energy. Okay, so it's a perceptive kind of quality. Yeah, intensity also I already told you. Power emitted per unit solid angle. The torch beam example I gave you. So yeah, transmission through matter, dispersion. These may basic definitions. Also reflection, refraction, and all like you know these things. So maybe I just Google these things once, and maybe next class when we do, I will jump into the basic setup of the AS, like what are the equipment, what actually happens in the AS, and what are the various components. Like so, there's an optical component, there's a detection component, right? There is a flame. We'll see. Okay. For now, I think this much is enough. Whatever end of hours has passed. Okay, so yeah, I'll also upload the problem sheet with this. Just you also just to solve that problem sheet. I think this week's assignment will also be very easy to you. There's no big numerical or anything. All directly from the notes. So do that. And if you have any doubt, feel free to ask in the forum. That's it, I think. I'll end the class. Thank you.